Hi, I am Mina Mourad, Assistant Professor at Mechanical Engineering Department, Shobra Faculty of Engineering, Benha University, Egypt. My research's interests are about wind energy, fluid mechanics, ventilation, air conditioning, turbomachinery, computational fluid dynamics. I have published some papers about wind energy, 2 papers, or 3 papers about wind energy, and 1 paper about vortex-induced vibrations on risers of petrol extractions. My master degree was about wind turbine wakes. My PhD was about winglet effect on wind turbine performance. I'd like to thank Mr. Sedef Budak again for this opportunity to share this knowledge. The requirements for this course or for this lecture, at first, this lecture will give you some introductions about wind energy world. We will explore the main items and the main scientific terms for wind energy field. In order to complete the course, if it is required from me to give advanced and more technical background. So at first, the origin of wind. What is the origin of wind? The source or the main source of wind is sun. Sun is the main energy source for all machines and all environmental impact, environments about us. Sun is produced about 4 by 10 power 26 joules of electromagnetic radiations. Just incidence from them 47%, reflected about 30% by clouds or by the surface. Let's select the cursor. Sun, if we get the 100% of electromagnetic radiation, Earth will absorb about 47% of them. The other are reflected up, or the others 23 reflected by clouds, 7 reflected by surface. The total is 30% reflected to the space. 19% absorbed by atmosphere layers, 4 absorbed by clouds. So we are talking now about the 47% of the sun, which incides on the Earth. 47% absorbed by the Earth or incident to the Earth. Just 2% of them drives waves and the currents, about from 1 or 2% which drives waves and the currents and winds and so on. So the main source of wind generation on the Earth is sun. Let's simplify the process. The process by assumption that Earth is not rotating. According to the Earth's alignments to sun, there are equators, there are North Pole, there are South Pole, and all these information that we have known. The region of equator is more hotter. The North Poles and South Poles are colder. So the main cold air with high pressure high temperature, high air with low pressure. So wind swell flows from high pressure to low pressure regions, and so on. These assumptions that the Earth without rotation. By the rotation of the Earth, by assumption, this rotation is counterclockwise. There are induced currents of air, additional to the main currents that moves based on temperature difference. It will known Earth, this velocity of Earth at equators is about 1,600 kilometers per hour. At North Poles and North and South Poles, it's about 0 kilometer per hour. It's a tangential velocity. So this motion of Earth will make the currents, the main currents that from the figure or this figure that is straight. It will be aligned in the same direction of rotation in both sides, from North Pole and South Pole to the equators. There are another currents of equators heat moves in the same direction of rotation of the Earth, will generate the inter-between currents. Let's say that these waves or this vortex, it will construct vortex from North Pole to equator. It will be a large vortex. This current will damage or will collide the long vortex that's found from North Pole to equator to construct another ferrule cell in between the polar cell and the Hadley cells. So the names now, it is supposed that if the Earth is constant without rotation, that it will be one vortex from North Pole to equator, one large vortex from North Pole to equator. The currents that feeding this region of a ferrule cell will make the counter-rotating cell or counter-rotating vortex that will be acted as air curtain effect, to simplify the expression, air curtain between the polar cell and the Hadley cell. So it will construct motion of North Pole to in the direction of equator till till at the mid of distance. The same here for Hadley cell. There is current from this region to the equator. The inter-between or the in-between cell is ferrule cell, is counter-rotating cell, is constructing due to the currents comes from equators or those due to Coriolis acceleration or Coriolis motion of Earth. Since the moving of winds is a combination between winds and the motion of Earth will produce a motion is called Coriolis acceleration. So this case is the actual case of wind's motion about the Earth. Since these cells, the equator is divides Earth into similar regions. This Hadley cell, this polar cell, ferrule cell, and so on. So the currents that we have talked before will produce vortex in this direction with counter the vortex in this direction and the vortex in this direction, and this position that will explained here in this figure, the three vortex. So the result is different currents according to the SE trade winds or the lines of Earth horse latitudes or 60° or 90° according to the lines or these lines. So, for example, the countries in North Africa will dominate or will under control of east-north winds. For the countries in Europe and in Europe with western or west-south winds with westerlies these northeast trades. So we can say that countries like Egypt will be under control of northeast trades of winds. But the countries in Europe and Turkey will be under control of westerlies due to this category of wind distribution, which constructed mainly by the effect of sun. This is the origin. The origin of wind around the Earth. This is the global motion of winds. These jet streams that we have talked before, that comes from equator to North Poles and makes the effect of air curtain effect and separator between the polar cell and Hadley cell. Okay, let's continue. This for flat, this is by assumption of flat Earth. This polar jet stream that acts as a polar jet stream and subtropical jet stream, which acts as or made the ferrule cell or the vortex or the separator between polar cell and the Hadley cell. But what about the secondary or periodic winds or local winds in the in a region? Due to our understanding from the previous slides, we know now that winds moves from cold places to hot places. Then they send the cold places with high pressure, but the hot places with low pressure. So the winds flows from high pressure to hot pressures. What for locally at what happens locally for same region or some regions in day hours in day hours the water will be colder than the earth or the earth or site. Since the wind motion will be from cold place or hot place to earth or to site with forward from this direction, and so on. The hotter air will be called upper or at high distance from earth, and then revised and cooled by air by water, and so on. The process will be maybe we may describe the process with a large vortex or small vortex between water and site or land. This during the day hours, but what happens during night hours? It will known that the capacity or specific heat of water is higher by 4 times of the specific heat of Earth. Since the specific heat of water is higher by about 4 times of Earth. So the waters can save energy and heat more than air. Since at night hours, we can say that warm water, that water will be warm due to the all-day heating of sun. But land, it can lose its temperature easily than water. So at night, the water will still warm, but land will be colder. So the process will be reversed. So at night, this is the reversed regions, or this motion is counter the motion of the hours. These local or secondary or periodic winds that can be existing at any place or local place between cold and hot places. Let's continue the periodic or secondary winds. Secondary or periodic winds can be existed at during the or between the high mountains and the valleys. The valley is region is lower with elevation between the mountain top. The mountain tops during day hours, the mountain tops will be with high temperatures, but the bottom of the mountains will be with cold air. So it will produce two vortices, one vortice or motion of air from with this direction. The cold air will it is heavier, since it will be descending to the bottom, then it rises due to the warming of air, and so on as the both sides. This is due to the daylight. But what happens at night? At night, the process is reversed, or it will be reversed. According to that, the tops of mountains will be cooler, easier, or cooler, quicker than the bottom of the mountain. Since the bottom of mountains will save the stored energy and the stored heat during all the day. Since the valley or the the bottom of the valley, it will have warm water, but the top of mountains will be cool with cool air, since it will be reversed motion, since the counter rotating vortices counter then the vortices or the motion of air during the day hours. I hope the previous slides which will explain. If anyone have questions, I am ready before entering to the another slides.
Okay, thank you, Dr. Mourad. Sorunuz varsa alabiliriz diyor hocam. If you like, you can write from the chat, or you can, raise your hand, and we can give you the time to speak. Otherwise, he will continue.
Okay. Let's continue. Let's go in more details about the wind energy in two countries. That is, my country is Egypt, and Turkey. Egypt is a gifted country with wind energy. Since the almost of energies or wind of losses around most of areas of Egypt it exceeds 10 meters per second. Since it is considered a high wind velocity, and we can generate more and more from electricity. Actually, according to remap analysis shows that renewable energy could provide 22% of Egypt's total energy supply in 2030. It is our plan or Egypt plan to 2030. Up now or till 2014, it will be the wind energy share or market share or energy share can be 5%, just 5%. But according to analysis and according to our plan to construct new wind farms and then to make a good contribution for wind energy in Egypt, because it is because of the existing of high losses around or especially along the coast of Red Sea. According for example, Ras Sedr, Abu Darrag, Zafarana, it is already existing a wind farm there. Ras Gharib, it is already existing wind farm there. Now, Z Gulf is already existing wind farm there. All this between the distance from Zafarana and Ras Gharib, it's about 1,400 kilometers. It is useful to construct wind farms there, and this Egypt plan to construct these wind farms for till 2030 according to the governmental plan. Electricity generation in wind energy market is projected about in Egypt. I am talking now about Egypt. It's about 4.46 billion kilowatt hour in 2024. It expected the annual growth rate. It's about 9.74% expected according to CAGR analysis. So with this growth rate, I think we can reach 10 billion kilowatt hour in 2030 year. This is for Egypt, but what about Turkey? About Turkey, it is country will invest in wind energy. However, the measure of countries accounts with by comparison with the two scales for Egypt and for Turkey. That is Turkey or most of Turkey regions has lower wind velocity relatively to Egypt, but they will invest, or the government will invest wind energy farms in Turkey. They produce or reach or production now in Turkey according to their needs. They need about 30 gigawatt total wind power capacity by 2030. But now it is already installed about 11 or 12 gigawatt according to different references. Actually, the production of Turkey is about 12 or 11 times the production of Egypt. That is may be because of the variety of wind energy, the large areas of wind farms that constructed, and many causes. Electric generation and wind energy market is projected to be in now is 42 billions or 43 billions kilowatt hour in 2024, with growth rate is about 4.21 is expected. Since the Turkey is at the last years well invested in this renewable energy, and this is a good a chance for all world now, or it is renewable energy in renewable energy at all, both of solar energy or wind energy. It is the challenge of all countries or all the world now, due to the wars and the news that we hear every day about the wars in many countries all around the world. Since the main reasons of war in all the world is energy. Since every country, so or Egypt or Turkey or others, their challenges now is to produce energy from renewable energy. That is because of the disadvantages. We will talk about this in the coming slides. Okay, let's go in more details about the theoretical concept of how to calculate the wind power, how it is calculated. According to my knowledge, that all of you are engineers, I think you will understand my speaking about these theoretical equations. According to mass conservation or mass conservation equation, dm by dt equal rho by a by rho density of air by area of any element in wind or u wind velocity. According to this volume mass flow rate, according to continuity equation, we can express the kinetic energy per unit time. The kinetic energy, it well known to be, it is one half mass flow rate by u square. What is the mass flow rate here? Is rho by a by u. Since so, the equation can be expressed in half rho a u cubed. So the result now that the available wind power at any region, the available wind power at any area, across any area, it will be one half rho a u cube. And so from there we can get the wind power density or wind power per unit area by dividing this equation by area, since the power per area equal one half rho u cube. Since the expression we now knowing or about to know two expressions. One expression is called available wind power across any area, and the power density or wind power per unit area. So the maximum power or the total power can be achieved by localing or positioning an area or disk across wind. But according to the theoretical, according to the next slides, we will see that we just take our wind energy maximum can harvest just about 0.59 from this complete power, or say so again that maximum, or according to Bede's theoretical method, the maximum power gained from wind energy or any wind energy, it will be about 0.59 from this power. From here, from the previous slides, the expression of wind power density is coming. According to wind speed 0, we can substitute in the previous equation. According to the wind velocity, we can express the wind power density. Since so, according to the wind velocity 0, there is power per area or wind power density equals 0. According to 5, wind power density will be 80. So the relationship between them is cubic. the cubic, if this linear increase in wind speed, it will be followed by cubic or cubic increase for power. So the wind velocity is a high important parameter on detecting wind site and the wind turbine, that we will know how to match the wind turbine, this wind turbine in this wind site in the next slides or in the followed slides. But now you have to know that the velocity is important parameter to detect the power of wind. The area or the diameter of rotor is considered is the second important parameter to increase the power of wind turbine or to reduce the power of wind turbine. Okay, what this theoretical or the main concept of the wind power or existing wind power or wind power density in any place. But what about wind power density from site? This is, I think, this is our job, this lecture, and if you permit to us to make another lectures, is the wind power density from site. All wind maps for all countries all around the world is already have wind atlas or wind maps, can be specified by wind velocity or by wind power density. We can produce the data from wind map according to, as I said, wind velocity or wind power density. How the wind power density from site is calculated? We all agree that wind power or wind velocity at any place is fluctuated. It is not continuous. It is according to turbulence, according to many parameters, according to season, according to many parameters. So there are fluctuations in wind velocity at any site. What is the solution for to get the wind maps or to get the wind power density maps? Here is the statistical analysis by localized or by located anemometers probes. Anemometer is the device which measures wind velocity. By studying a specific site, we should localize some anemometers around the site. The anemometer, it will take average velocities across 10 minutes. By default, or it is well known that wind velocity fluctuates across the 10 minutes. The anemometer will take some readings across 10 minutes, and so it will make average for these readings across 10 minutes. By averaging across 10 minutes, we can get average hourly averages of wind velocities. The hourly averages, it is described by U prime. UI, it is itemized or the instantaneous wind velocity. But by averaging the U or U velocity, we get U prime. Q prime is the average wind velocity or hourly averaged wind velocities. It is multiplied by KE. What is KE? It is energy pattern factor. Energy pattern factor. It can be considered. It is the mean for the wind energy readings across period. How it is come? KE is summation of UI, the instantaneous velocities, cubic instantaneous velocity, on divided by its the readings numbers. Let's say, let's talk about 10 wind velocity readings. 10 wind velocity readings. It's about 10 velocity readings. We will have different values. We will sum the cube of each velocity reading or speed readings, and then divide by the 10, the 10 or the number of these readings, and then divide by U average cube. This is KE, the energy pattern factor. This is a statistical method to calculate the power density that is already existing in the site. We can not measure or to visit a specific site and measure the wind velocity there by the probe for 1 day or for 2 days or for 1 week, and we can determine the wind velocity or wind power density in 1 week or 1 month or 1 quarter. It is a fatal mistake, but the readings, it should be taken about 1 year. It can be calculated by hours, about 8,760 hours. Yeah, we can take the readings or these probes according to climatic conditions. The probes have the same position, give readings for the sites. So any site cannot be studied less than 1 year. So 1 year, it means 8,760 hours. We can calculate now this average is given about over 8,760 hours. Then we can calculate the power density or average power density from the site. We can detect according to classes. Power density minimum than smaller than 100 watt over meter square is low power density. Power densities that equal 400 watt per meter square is good. What power density is greater than 700 watt per meter square is great. So the regions or sites with power density lower than 400 is not good to construct wind farms. It is starting from 400 to 700 or and more than these values, we can construct wind farms. For example, the mean or average wind power density in most of regions in Turkey, it's about 400 watt per meter square. In Egypt, it's wind power density. It's about the average of lands. It's about 600 watt per meter square. So the two countries is suitable to construct wind farms and to construct more and more. This another classification according to the wind power classes. With more classes, resource potential or the potential or poor or super, wind power density. All these, by the for our knowledge, all these measurements is taken at specific height from land. It's about all these readings. It should be detected or from 50 meters from land, from sea level, or 100 from sea level. All wind maps or wind atlases from any site on the network, you can find or you can get the readings of wind power density at your country or your state from 50 meter
Dr.
or
Mourad, can I add something on this page into your experience, if you don't mind, about the wind power classifications? Because we, in Turkey, we have the complex sites. So we have the rough and the geographically and the high sites, and also the steep sites, and the obstacles are quite, high. And
yes,
at the moment, also the wind turbine manufacturers, they are, continuously increasing the capacity, the production capacity of the turbines. Plus,
right.
they are extending, enlarging, and the light. The increasing the height of the tower, the blades, and etc. So because of that, at now also the most popular measurement towers and the measurement systems are currently starting from minimum 100 meters up to sometimes 150 meters, because on the sites we are trying to measure the winds from the correct level that we are going to replace turbine, to be able to calculate the energy production. So the turbines and the measurement towers, they are getting bigger and taller. I don't know how long it will go, but it is it is. It wasn't like previously when I started. It was only 10 meters, 20 meters. Now it's 10 times more. And so yeah, Egypt is comparing to Turkey is quite flat. So you are quite lucky on that perspective. But in Turkey, as you showed the map previously, where the most high winds is, they're all complex sites, a lot of mountains, top hills, and near the sea there is a lot of also air density and the pressure. So in Turkey, we quite developed, because we are doing it maybe for 15 years, but it is quite rough area for us to work.
Right.
Mm-hmm.
You are right. I respect your this insight that is already performed now. It's already 100 or at elevations 100 meters from sea level, according to the geographical obstacles and the mountains and hills and so on. But I say, or I speaking about that we can measure, or we can extract the data from any site about at any elevation, or if we can get the data from site at elevation, it's about 50 meter, we can get at elevation 100 meters, 150 meters, and so on. It is not just we mustn't put the props on towers with height 100 meters. You can just measure the wind velocity at 50 meters, or props or anemometers at 50 meters height, or 25, and then by the next slides we will see how we can calculate according to the geographical obstacles that existing here at the site. That is just example. That is a demonstrative example. This example is speaking about a wind turbine with 12-meter diameter in wind regime with average velocity with wind speed 8 meters per second. I say I am speaking about average wind speed. On average wind speed, that means that is not measured from that is not instantaneous velocity, but it is average wind speed that is measured annually. By assumptions that rho, or density of air, it's about 1.225. As a turbine efficiency, it's about 0.4. It is required from here the annual energy production in kilowatt hour. What is that is energy? if we construct wind turbine with power, with a specific power, it is just the maximum power can be gained. But how about, or what about the energy can be extracted from this turbine? It is our scope. The energy that extracted from this wind power, it is can be gained by the power to calculate the power from the diameter and then multiply it by efficiency. We will explore or understand more complicated problems in the next slides. But we can calculate the power, the maximum power, or the maximum power can be gained from wind turbine with diameter 12 meters by efficiency by 8,760 hours to calculate the average annual energy production in kilowatt hour. This by assumption that the wind turbine will operate at its nominal power, its maximum power, all days of the year at 8 meters per second. It is this example. It is just a demonstrative example, but for more understanding, as we said, that we just make probability density. We will see it at the end of the lecture. But now we just calculate the power from the available wind power. The turbine efficiency, it can be considered the power coefficient. We will see what is the power coefficient. We can consider it efficiency now by multiplying power by efficiency by number of hours. We can get the annual energy production from this turbine around 1 year. But this value is considered by considering 8 meters per second is constant all the days, all hours, or all the 8,760 hours all the year, and that not occurring. So the result here is 124,300 kilowatt hours. It is the region of the energy production. How to calculate what is the meaning, what is the difference between the kilowatt and the kilowatt hour. Kilowatt hour, it is energy produced or energy consumed. It is multiplied by the operation hours, then we can the energy production. But the power, it is the ability to do work. Okay. There are, according to effect of elevation, that is the problem that we have talked in the previous slides. There are two approaches to calculate or to predict the wind velocity at a specific elevation. There are atmospheric boundary layer according to log law. There are power law profile. Let's see the atmospheric boundary layer log law. Atmospheric boundary layer log law. It is considered, it is a log law, it is depending on the boundary layer that existing. Boundary layer, it is for any engineer will know about fluid mechanics. He will know the boundary layer. It is a layer that adjacent to any surface, and it has more viscous effects, and viscous effects are existing at these layers with highly than the out regions of the boundary layer. So the boundary layer is a region that is adjacent to the surface of wind flowing to the surface. It is to scale. If we speaking about the boundary layer of air moving over a flat plate with heat for heating, it's about 1 meter length. Boundary layer, it is not exceeds 1 millimeters. Boundary layer thickness, it not exceeds 1 millimeters. But if we're speaking about wind losses or over lands, the boundary layer, it can be reached by meters, like here that for centers and city and the tall buildings, the boundary layer can be considered by 3 meters boundary layer thickness. So therefore, it is boundary layer thickness. It is to scale according to the scale that we have talking about. So the boundary layer or the log law is considering the boundary layer in its calculations. Since Z node, it is the roughness or the boundary layer thickness that is existing according to the topology of the region of the site. If we have very smooth or ice or mud, it is Z node equal 0.01 millimeters. If we're talking about crops or few trees, it's about 100 millimeters. If we're talking about center of cities and with tall buildings and the skyscrapers, we can speaking about 300 millimeters. That's what we consider Z node by 300 millimeters. 3,000 millimeters. 3,000 millimeters, that is not meaning that the building tall is 3 meters. No. 3,000 millimeters, that meaning that the Z node equals 3 meters, but the meaning of 3 meters is comes from the boundary layer thickness. So the boundary layer thickness is depending on the roughness that existing in the site. By easily ZR, it is the reference that we already measured. If we measure or citing probes to measure wind speeds at 50 meters, so ZR, it will be equal 50 meters. The required elevation to measure the wind speeds is 100 meters, so we will put Z equal 100 meters. So we will come the measured velocities at 50 meters, and we will get the U of Z or the U at 100 meters. This is the log law. This is the log law, our boundary layer, depending by considering the boundary layer effect. What about the power law profile? It is more easier. It is not considering the topology into its considerations or into calculations. It is the ratio between U and UZ or UZR. UZR, it is the reference wind speeds that is measured at 50 meters, for example. UZ is the required wind velocity or wind speed. Z over ZR is the same. It is the ratio between the elevation or the required elevation or the reference elevation, 500 or 100 over 50 hundreds. By considering power law or power law profile, since it is considered alpha, the power is 1/7. 1/7 indicating the according to Schlichting 1968, it is considered the velocity profile that is existing in the turbulent boundary layer. We have known about fluid mechanics that there are calculations for laminar boundary layer and the turbulent boundary layer. Laminar boundary layer, it can be solved by Blasius solution or exact solutions or approximate solution by considering the velocity profile. But turbulent boundary layer, must be solved by approximate solution by considering wind power or wind velocity profile. The wind velocity profile for turbulent boundary layer with order or power is equal 1/7, according to Schlichting 1968. But the problem here for power law profile, it is not considered the roughness effect or the roughness effect or the or the topology or geographical effect or geographical site of site. For example, let's see, to determine wind speed at high 40 meter over surface terrain of few trees, since here the topology of the site is, or the geographical effect is, there are few trees. If the wind speed is at height, is measured at height 10 meters, it's known to be 5 meters, we can use two different methods. The first method, the simple logarithmic wind profile, by considering the wind tree's roughness. The few trees roughness is 100 millimeters. Let's see, Z not equal the roughness is 100 millimeters. That is mean 0.1 meters. For U of 40 equal, to calculate the velocity of 40, easily we can substitute in the previous correlation. We can get, or we can calculate the expected wind velocity at elevation 40 meters by considering the wind velocity elevation at a specific or measured at 10 meters. It will be 6.51 meters per second. The second method, or the power law profile, it will not consider the expression or the few trees that exist. By substituting, it will be calculated to be 6.09. There are a difference between 6.51 and 6.09 meter per second. If we change the geographical obstacles that is existing in the region by the first method, if the trees cut down, assume rough buster of surface terrain, or and so on.
Are you there, Mr. Mourad?
Kayıt dondu.
Ha, dondu değil mi? Evet, hoca dondu sanıyorum. Bekleyelim, bağladı tekrar. Bağlantısında bir şey olabilir. Evet, hoca düştü. Tekrar bağlayacağız arkadaşlar. Bir iki dakikanızı rica edeceğim.